So starting with new material today, this is Math 150, Multivariable Calculus. I've got lecture 9. And what we're going to do today is we're going to be talking about different optimization problems. So we've already done, I think, me running into the blackboard. Yes?
Yes.
Okay, good. Given that my right arm, I think, might actually be broken, I don't want to do that again, so I'm glad that I don't have to. What was that to emphasize? You should check your endpoints. Okay, it's not enough to just look for where the first derivative is 0. Now, the first derivative being 0 is a very nice condition for a candidate for the maximum and minimum. It does not mean that you have to have a maximum and minimum. If I give you f of x is x cubed, f prime of x is x squared, you have a critical point. F prime of x equals 0 implies x is 0. But x equals 0 is not going to be a maximum or minimum. If you plot this function, it's going to look something like this. And what's going wrong is f prime of 0 is f double prime of 0 equals 0. And so what is going on here is that it's neither a maximum nor a minimum. The trouble is the second derivative also vanishes. And this leads to the second derivative test. Now, you can test things with just the first derivative. How many of you have done first derivative tests and stuff like that? Okay. So if I give you some critical point x naught, where the first derivative is 0, if the first derivative is positive afterwards and negative before, I have an idea what the function looks like. If the first derivative is negative, the function is decreasing. If the first derivative is positive, the function is increasing. So if I were to plot this, you can do a little plot like this. Here's x. It's got to look something like this. It's got to be going down until we come here, and then up if we come afterwards. So that's the first derivative test. What about the second derivative test? Well, imagine I have f double prime, and imagine f prime is 0 at x naught. So we have a critical point. This is a candidate for a max or minimum. It's not guaranteed that it's a maximum or minimum. Imagine the second derivative is positive at this critical point. If we assume things are continuous, if you move just a little bit away, what's going to be what's going to be the sign of the second derivative? If it's positive at x naught, what's it going to be a little bit before and a little bit after? Still positive. So I know in some small little neighborhood, it's got to be positive. So if the second derivative is positive, you can view the second derivative, if you wish, and I so wish, as the derivative of the first derivative. The first derivative tells you if the function is increasing or decreasing. So the second derivative will tell you if the first derivative is increasing or decreasing. If the second derivative is positive, what do you know about the first derivative? Has to be increasing. So if it's 0 here and it's increasing, it's got to be positive. Well, if it's increasing to 0, what does it have to be before 0? Decreasing. And here's the second derivative test. If the second derivative is positive and the first derivative is 0, then the first derivative looks like this. And then you know, it's got to look something like this. And you have to have a minimum. So really, the second derivative test is just using the first derivative test. What I like to do is minimize how many things I have to remember. Can somebody give me a nice, easy function to think of that has a minimum? X squared. Can somebody give me a nice function to think about that has a maximum? Negative x squared. Right. Take simple examples. F prime of x is 2x, so the critical point is x equals 0. G prime of x is negative 2x, so the critical point is also x equals 0. The second derivative at 0 is just 2. The second derivative at 0 here is just negative 2. And I know what this function looks like. This is the up parabola. This is the down parabola. Here's how I remember the second derivative test. All I have to do is I have to remember there's something about the sign of the second derivative that tells me if I have a max or a minimum. Which way does it go? Well, let me test it with the parabola. I can tell if the parabola is up or down by whether or not it's x squared or negative x squared. And I see, here we go, this is a minimum. So if the second derivative is positive, it has to be a minimum. If the second derivative is negative, it has to be a maximum. And that's the second derivative test. Okay? What we're really doing, and we will do more about this when we get to Taylor series, is we are approximating a complicated function with a simpler function. So the big thing in calculus was the tangent line. And you take some function, and at a point, you approximate it by a line, and the line does a pretty good job over a small period. What do you think would do better than a line? What do you think would be a better approximation than a line? Polynomial. Which polynomial? Which should we go to next? X squared. Well, not just x squared, but we could do a parabola. And then what we could do is, what is the best approximating parabola locally? And then what's the best approximating cubic? This is where Taylor series come from, trying to replace a complicated function with a simpler one. And so if I have a parabola, and I want to figure out, is it an upward or a downward sloping parabola? Well, I can write my function f of x as f of 0 plus maybe f prime of 0 times x plus f double prime of 0 over 2 factorial x squared. And this is an approximation. And if I look at what happens, if I put in x equals 0, I get f of 0 versus f of 0. Good. If I take the derivative of both sides, the derivative of f of 0 vanishes. The derivative of this piece is just 2x, which is 0 when x equals 0. So the derivative of the right-hand side at 0 is just f prime of 0. It matches this side. If I take two derivatives, these two terms vanish. And now you can see why I have a 2 factorial down here, because when I take two derivatives, I'm going to have 2 times 1. And so the second derivatives match. So what I'm doing is I'm trying to find what parabola approximates my function. If I wanted to have a cubic, I would have f triple prime of 0 over 3 factorial. And now let's look at what happens at a critical point. At a critical point, what is true about this? It's 0. And all f of 0 does is it just shifts things up and down. Right? I might even be able to do this. I can just shift this camera. Whoop, ooh. It did not like that. Okay, we will not do that at 11 o'clock. I can just shift the camera up and down. It's not going to change the relative behavior of things on the table. I'm just shifting everything up and down. The real behavior is coming from this. So if the second derivative is positive, then what this means is as I get further and further away from 0, I'm getting larger in both directions. I have a minimum. If the second derivative is negative, then as I get further away, I'm getting smaller. I have a maximum. So the second derivative test is really just coming from looking at the best approximating polynomial of degree 2. When we get to more complicated functions of several variables, it becomes a nightmare in terms of how do you tell if you have a maximum or minimum, what is the second derivative test? If you knew which class, would it be really easy for me to teach you the second derivative test? Linear algebra. It's one line. And this is why we care about matrices. It's one line if we know linear algebra, we don't. So at some point later in the semester, I might talk a little bit about this, but this is a little placeholder, that the second derivative test is clean in one variable. Is it positive, is it negative? In two variables, it's more complicated. These two, is this partial derivative positive and is this product positive? It's more involved. All right. Any questions on what we've done so far? Okay. So one of the other questions that was asked was how do we set up equations for optimizations in several variables? How do we find maxima and minima? One of the big things that you need to know before you're searching for an object, what would you like to be true before you start spending your time looking for something?
It can be found.
It can be found that it's there. One of my favorite comedians is George Carlin. I have allowed my kids to listen to the uncut versions of a lot of his routines. He is a master at language. And he has a wonderful routine where he is explaining how the airline industry does not understand what words mean. And he talks about, a near miss is not what the airlines think. Oh, look, those two planes nearly missed. That's actually bad if they nearly miss. A near miss is a hit.
Because they almost missed.
Correct. One of the things he talks about is, please check your immediate seating vicinity for any items you may have brought on board. I may have brought on board my grand piano, but I didn't, so I'm not going to look for it. I'm going to look for the things I did bring on board. When you are searching for maxima and minima, you would like to know that they exist to be found. Not every function has a maxima and minima. And that's one of the real challenges. If I give you the function f of x equals 1 over x, 0 less than x less than 1. If I plot this, it's asymptotically going to plus infinity. This function does not have a maximum value. And so if you try to find a maximum value for this function, you're going to be disappointed. So there are results in which class? About the existence of these maxima and minima. No, actually it's real analysis. This is one of the few times when it's not linear algebra. Real analysis will prove to you that in many situations you must have a maximum and a minimum. So if you try to do this stuff, it's going to work. So we're not going to worry so much about that. We'll just do the material. So for a lot of situations, there are two possible places for the maxima and the minima. They can be on the boundary, or they could be internal. If they're internal, it's the same as Calc 1. We look for places where the derivative is 0. The difference now is the derivative has more than one component. So for the interior, we want the derivative of f, or the grad of f, or gradient of f to be the 0 vector. And again, these are all different ways of writing the derivative. So we want df dx to equal df dy to equal df dz, for instance, if we're in 3 variables. Because if they don't equal 0, then just go in one dimension. Say df dx is not 0, then it's positive, say. If it's positive, I'm increasing if I walk in this direction, so I can't be a maximum, and I'm decreasing if I walk in this direction, so it can't be a minimum. So if df dx is not 0, it can't be a maximum, it can't be a minimum. Similarly for df dy, similarly for df dz. If all 3 of them are 0, does this mean we have a maximum or minimum? No. I could probably give you maybe the function x cubed, y cubed, z cubed, right? My gut feeling is that's probably going to be problematic. Because it's problematic if I view it just as x, y, or z. Oh, but maybe not because they're being multiplied. So maybe if I did something like maybe x cubed plus y cubed plus z cubed, maybe something like that would be a good problematic function. So leave it as an exercise for you. Come up with a nice function in 3 variables that doesn't have a maximum or minimum at the origin. Yes?
What was the difference between those two df's up there?
Which df's?
Oh, it's a triangle.
Triangle.
It's an upside down.
It's an upside down.
Oh.
I love the fact that we call it an upside down triangle. As opposed to...
It looks like an upside down triangle. This is like an upside down delta.
Right, and so you're imposing your orientation on... I mean, again,
Right.
everybody does this. Everybody calls this the upside down triangle. But really, it's a triangle. But it allows us to distinguish the 2 different triangles. How many people know LaTeX? If you know LaTeX, the way you do mathematical writing, it's like /nabla. And then it has a nice command, and so you can just refer to it that way. These are all different ways of writing the derivative. So these would be, as a vector form, df dx, comma, df dy, comma, df dz. And just writing it as a vector. And if we're in 4 dimensions, we would have 4 components. So to find the interior maximum and minima is not that bad. To find the exterior ones, the ones on the boundary, that's much harder. And this is where we use the gradients and Lagrange multipliers.
Wait, I do have a quick question.
Yes.
So Because I know not all, this doesn't just determine if it's maximum, and then do you take the second derivative of this, if you're just working with
So
interior?
I'm not talking about the second derivative test right now.
Okay, just
Right
first
now,
derivative.
these are our candidate points. For a
Okay.
lot of problems, it should hopefully be clear if you have a maximum or a minimum. A lot of times, if you're trying to build an enclosure, you know that area is 0, and you're not going to be able to get infinite area, so whatever you get, that's going to be the maximum. There is some physical maximum. But technically, you need a result from real analysis to say that. Right. The difficulty is how we deal with things on the boundary. How many people have taken an econ class with Lagrange multipliers? Okay, how many people are going to be econ majors, at least in theory? You will hopefully eventually get a class with Lagrange multipliers. This idea of constrained maxima and minima. And this is where we have all the language from curves from before, that we need to figure out a way to talk about how can we maximize things given our constraint. So for instance, I might be at a point where it's not the maximum value for the function, but I have to stay on a certain level set. I have to stay on the surface of the sphere. And so maybe I have a situation where I'm on the sphere, and the value is equal to 1000z. Where would you like to go? You want to maximize this function. Where should you go? So you're on a sphere, centered at the origin. Where should you go? Where is this function largest?
On the z-axis,
On the North Pole. Where's the function smallest? South Pole. If you went higher, if you went above the sphere, would you have a larger value of the function? Yeah. But if you have to stay on the sphere, you can't go above it. So the best I could do would be to go to the point, 0, 0, r. And this is what we need to figure out. How do we deal with these constraints? That in an ideal world, if we had no constraints, we could travel wherever we want and get the function to be larger and larger and larger. But because we have a constraint, we have this constraint g of x, y, z is x squared plus y squared plus z squared minus, say, r squared is 0. That forces us to live on a sphere of radius r. And so if we're living on a sphere of radius r, we can't just go to the highest possible value of z. We are stuck. So can anybody tell me geometrically what the derivative of f or the gradient of f represents?
Change in each variable?
So it's df dx, df dy, df dz. So it's going to be related to the change of the function. So if all the components are positive, then as we're moving in this direction, things are getting really large. If all the components are negative, we're getting really small. It basically tells us what direction should we travel to see the greatest change in f. It's the vector that represents how f is changing. So if I go in that direction, I'm going to see the greatest change in f. Which direction should I go to see the greatest decrease in f? Well, so I'm telling you that maybe this is the direction where my function is increasing fastest, increasing the most.
Should go to the opposite.
So I should go the opposite. So if I go in the opposite direction, it'll be decreasing the fastest in that direction. And so what's going on with constraints, if I give you like an ellipsoid, this would be maybe the equation g of x, y, z. Maybe it's x over a squared plus y over b squared plus z over c squared minus 1 equals 0. I have to stay on the ellipsoid. And I might want to see where's my function largest on this ellipsoid. The gradient of g is going to be the normal to the surface. So it's normal to the level set of 0. It doesn't really matter if I say this equals 0 or 5 or 20 or whatever. Because when I take derivatives, that's going to vanish. In terms of evaluating things, the actual value, yes, will matter. And so the way you should think about it is the gradient, grad g, is the normal to the surface. It's perpendicular to the surface. So it's pointing out from the surface. If you want to stay in the surface, you have to go perpendicular to it. And so all of these constraints are the following. If I give you some surface like this, here is the gradient of g pointing straight up. So if I stay on the surface, I have to be moving perpendicular to the gradient of g. Imagine I tell you at some point that the gradient of f is pointing in this direction. So now we're going to use some basic properties of vectors. So here is the perpendicular to the surface. Here's the gradient of f. Is the gradient of f tangent to the surface? Is it? No. So what that means is I can break this up, and it has some part tangent and some part in the direction of g. What that means is if I move in this direction, is my function going to get larger? Yes. And if I move in the opposite direction, my function is going to get smaller. So if the gradient of f has any amount in the direction of the tangent to the surface, into one of those tangent directions, it can't be a max or a minimum. Because you can just keep moving in that direction. You can think of this always in one dimension. So if the gradient of f is not aligned with the gradient of g, it can't be a max or minimum. So if I want to find a candidate, what direction must the gradient of f point? If I want a chance to be a maximum or minimum. So we just said if it has any component in a tangent direction to the surface, it can't be a maximum or minimum. So what direction must the gradient of f point? Perpendicular to the surface. And what is the direction that's the perpendicular to the surface?
The same direction as the g gradient.
The same direction as the gradient of g. So this is where Lagrange multipliers come from. That if we want to find candidates constrained max min, Lagrange multipliers. So we have g of x. I'm going to do it as a vector like this because I don't know how many components I have. I have some constraint, and I want to find the max or the min of some function f of x. So I need to solve g of x equals c, and the gradient of f at our point x is equal to some number times the gradient of g at x. If you think about why we're using lambda, there's a couple of reasons. Anybody know what letter lambda corresponds to? So lambda is Greek. What letter do you think lambda corresponds to? L. And we're doing Lagrange multipliers. Right? We also use lambda in linear algebra for eigenvectors and eigenvalues. You'll see it in the situation there. This does not guarantee that you have a max or minimum. It just says, here's your way to find them. So if we have three variables, we have x1, x2, x3, we have 4 unknowns and only 2 equations. This should scare you. But this is actually a vector equation. How many components does the gradient of f have? If we have 3 variables, x1, x2, x3, how many components does the gradient of f have? df dx1, df dx2, df dx3. This has 3 components. Right? I'll use x, y, and z. So we do it as x, y, z, and lambda, we have g of x, y, z equals c. We have df dx equals lambda df dg dot 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 df dz equals lambda dg dz. We actually have 4 equations and 4 unknowns. We have a chance to solve it. Of all these unknowns, x, y, z, lambda, which is the one you care least about? So lambda. We're trying to find the point x, y, z. Lambda is a helping unknown. We're making the problem in some sense a little bit more complicated by introducing lambda. At the end of the day, do we care about the value of lambda? No. Now, in economics, they will often talk about the interpretation of lambda. And knowing that value can actually give you some information. But if we're just trying to find the point x, y, z, we do not need to know the value of lambda. This is the least important. However, by putting it there, it often makes it easier to find the x, y, and z. And then the question is, how do we just go through the algebra and find the best answer? So there's a lot of different problems we can do. I'm going to start off with one of my favorites. So what was the children's book I read from? Click, Clack, Moo, right? How many of you have ever read Click, Clack, Moo or had that read to you? Great book. And there's actually sequels to the book. It's a wonderful series. Okay? So the Farmer Brown has a problem. Well, he actually has many problems, but the one we're concerned about is that he loves rectangular pens and will not consider anything other than a rectangular pen. And he has a certain amount of fencing. Let's say that he has 40 meters of fence. So x plus y is the semi-perimeter is 20, and you want to maximize the area, which is x times y. And the way you normally do this is you say, well, y is 20 minus x, so we want to maximize now x times 20 minus x. And when you're trying to maximize x times 20 minus x, what rule should we use to differentiate? So how should we differentiate x times 20 minus x? Simplify first. Don't go to the product rule. Simplify this. This is just 20x minus x squared. So if we call that a of x, we get a prime of x is 20 minus 2x. So the critical point is x equals 10. And you get that it's a square. Should I check the second derivative? Yes. If I check the second derivative, I'll see a double prime is minus 2. And the second derivative will tell us that it is a maximum. Does it seem reasonable that the maximum is a square? Does that seem reasonable?
That the maximum is a square?
Yeah.
Well, isn't that what you're finding?
Right, but I'm saying at the end of the day, you always want to ask, is this answer reasonable? I've just gotten that the answer is a square. Does that seem reasonable? Yeah, you could actually do the calculation. If you liked triangles, what do you think would be the best triangle? Equilateral. And if you had a 5-gon figure, the best 5-gon figure would be a regular pentagon. And in the limit, what do you think would be the best? If you could do any curve, what curve do you think would be best?
Circle.
Circle. And this is called the Isoparametric Problem. What region encloses the most area for a given perimeter? My wife was a graduate student at Wharton years ago, and they were building a new facility for the professors. And it was built very differently than most buildings. It was actually built cylindrically, not with right angles. I'm going to be careful because this is being recorded. What do people often like if they're powerful people? What kind of office? Who said corner first? Right? Corner office is a big status symbol. If you have everybody moving to a new building, you have a lot of big guns, who gets the corner office? There is no corner office, it's a cylinder. So, we're not sure if this is exactly why it was done, but one of the nice upshots of that is there were no corner offices to fight over. It does enclose more volume for a given perimeter, or for a given surface area, sorry. All right, I'm not going to go through the calculation now. I think we did Aquaman in the video. And what I love about that is if you have a river now, what should you do? Well, you can imagine you have twice as much fence and you're just doing it above and below. And I love using symmetry like this to quickly solve the problem. And so we do this in the video, and by doing this we see that it's now a rectangle that's twice as long as it is wide. Let's try to do this using multivariable calculus. So our function a of xy is the area, is just x times y. And our constraint is the semi-perimeter of x times y, of xy is just x plus y minus 20 equals 0. So this is basically our f, this is basically our g. What is the gradient of f? This is df dx, df dy. So what's df dx? Y. I need to know the answer.
What?
Huh?
Wait, sorry, what?
What's df dy? X. Out of curiosity, how many people know the Who's on First routine?
I've heard it.
How many people have never heard Who's on First? Okay. Voted by many the greatest comedy routine of all time. All right. What is the gradient of s? So that would be ds dx, ds dy. What would be the gradient of that? So what's ds dx? What is ds dx?
Just one.
Just 1. I'm taking the derivative of this with respect to x. What's the derivative of x with respect to x? 1. What's the derivative of y with respect to x?
0.
Derivative of negative 20 with respect to x?
0.
It's just 1. Similarly, what's ds dy?
1.
This is really nice. The gradient of s is fixed. It's always the vector 1, 1. So now we need to solve the system of equations. X plus y minus 20 equals 0. And then we need y equals lambda times 1. X equals lambda times 1. Can I divide and get x over y, or y over x equals 1? So can I just divide at this point? Why not? Why can't I just divide? Why can't I just say y over x equals 1? What is the possible concern?
Oh, if x is, yeah, 0.
Yeah, if x is 0 or y is 0, we're in trouble. So we can do two cases. Case 1, x equals 0. Well, if x equals 0, what does lambda equal?
0.
So we then get lambda equals 0. If lambda equals 0, now what do we immediately deduce?
Y equals 0.
Therefore, y equals 0. Therefore, x plus y minus 20 equals negative 20 is not 0. Not on constraint. So do we have to worry about the case x equals 0? Yes, but it's not going to contribute a candidate. I much prefer breaking my problem into a lot of smaller problems where I have additional facts at my disposal. When I'm looking at this, I would love to divide this equation by this equation. If I divide this, what variable goes bye-bye? Lambda. Lambda goes away. But I have to be careful. Well, what if lambda is 0? What if x is 0? So I handle that separately. Now I can do case 2. X does not equal 0. So if x is not 0, lambda is not 0. So now I get y over x equals 1, so x equals y. I have 3 equations and 3 unknowns. I have to use all of them. I've used these 2. Which is the one equation I haven't used? the first one. So now I substitute into x plus y minus 20 equals 0. We get 2x minus 20 equals 0. Therefore, x equals 10. And now that we know x equals 10, we immediately get y equals 10 as well. And this is how we would set up and attack a problem like this. So for this problem, we could actually do a backdoor, and we did not have to use multivariable calculus to solve it. We were able to sneak it around, and we were able to instead convert it to one variable by replacing y with 20 minus x. You can often do this for a function of two variables. But if you have 3 and higher variables, you're not going to be able to keep doing this. Or it's going to start to get more and more complicated as you consider more and more different things. It's much nicer to just look at it like this. What I think we'll do is I'm thinking about adding an extra lecture to the semester to just do more on these optimization problems, because there's a lot of really good stuff here. So what I might do is I might move the method of least squares lecture to next week, and then just do more optimization right now, just because this is such a good, important topic. We rush through too much material, and the stuff that you actually might use in your life, we go through at warp speed, and this just doesn't seem right. So let's do that. We're going to add an extra lecture on optimization. I don't want to rush through this. So we want to think about more and more complicated problems that we can look at and how we might try to attack them. Okay. The other question that was asked was to go over the drowning swimmer problem. So let me maybe just say a few words about that, and then we'll spend the time doing some more optimization stuff. So I will shift the homework back. Well, no, we'll keep the homework due when it is. I'll just change when the next homework is due. So drowning swimmer. Anybody ever serve as a lifeguard? Okay. If you have been taught this, in some sense that's great, but I will assume that you do not save swimmers like this.
Using the
The theory of the drowning swimmer. So we have our lifeguard, the little board, and we have the poor little person drowning in the water. What is the lifeguard's goal?
Save their life and get there the fastest.
Right, so the goal is to save the life. How do we save their life? We get there as fast as possible. And so there's a couple of paths you can do. Any Monty Python fans?
Yes.
Okay. So this path is right out, where you run straight to the edge of the shore and then swim like this. This is essentially the worst reasonable path you can take. You're minimizing your time on land, you're maximizing your time in the water. We will assume that this is a normal lifeguard that runs faster on land than swims in the water. What you might say is, well, why don't I take this path, where I maximize my time on land and minimize my time in water? This is a natural candidate. Anything beyond these two paths is just not worth considering. If I were to run over here and then come backwards, that's stupid.
Well, if there's the current.
Well, if there's a current, or if there are people, right? Hopefully you have somebody who's running, defense in front of you and getting people out of your way to clear the path. But what we could do is we could say, let's run to some point here, and then from here we go at an angle. And so the path bends. And if you want, you can always normalize so that this is 0 and this is 1. And we're choosing our units. Once we do that, I no longer have freedom as to how far back you are over here or how far up you are over here. If I want, I can call that maybe this is A units, this is B units. And then it all comes down to I find a value of x. And for each value of x, I calculate what is the time. So I have some function t of x. And I just want to see what value of x makes the time smallest. And x is going to range from 0 to 1. And then we look for where t prime of x equals 0. And we find the critical point. And that's going to turn out to be the best place to go. And it's not going to be either of these paths. Another natural one is this path, where you run straight to the swimmer. Is this what you would typically do as a lifeguard? Basically, you see where the swimmer is, and you just run directly for them. The change, the amount of time you're going to save is negligible. It's not bad to know a little calculus and adjust your path a little bit. But, we're not talking about anything important here. We're just talking about saving a drowning swimmer. If we were talking about people running bases in baseball, now this is something that has potential playoff implications. And Professor Johnson in our department with some of our colleagues, you actually analyzed, if you're going to try to go for a double, if you want to just get a single, you just run straight to first, because you can overshoot first base. But if you're going for a double, people often start and then they swing out a little bit and take a little bit of a looped path like this. Why are you doing this? Well, because as you go from first to second, wow, if you're going straight like this, you now have this sharp change in acceleration. And sometimes it's actually better to take a more winding path because of how that's going to affect your acceleration and your speed. So for something like that, those few seconds will make a huge difference. For the drowning swimmer, I don't think it really matters. I don't think we have to do the calculus problem. What I like is if you do the algebra, you end up getting, I believe, a polynomial of degree 4 where you have to find the roots of a quartic. Roots of a quadratic aren't too bad. We can all do the sing-song negative b plus or minus square root of b squared minus 4ac all over 2a. There is a formula for the cubic. There is a formula for the quartic. There is no formula for degree 5 and higher. You can't write down the solution just in terms of the roots. So, great problem. What I love about this is that the optimal answer and your intuition don't differ by enough to really make it significant and worth doing. But if you were doing this many times over, then a small efficiency would make a difference. All right, so the last thing I want to do is I want to leave you with an optimization problem. It will seem silly because it is, but it turns out to have a really interesting application. All right, so the last one for the day. Given a number, if you want to do 100 for definiteness, I want to write S as A1 times AN. Each AI is a positive integer, and I want to maximize the product A1, A2 to AN. Note, you can choose n. So if I gave you the number 1,000 or the number 50, you might have a different value of n. So how would you solve this problem? So I will let you think about this. Oh, and I forgot to say, sorry, these should be plus signs, not times signs. Otherwise, they're the same thing. I want to write 100 as a sum of n positive integers. And I want their product to be as large as possible. So can somebody give me one way you might do this? It doesn't have to be right.
100 plus 0.
100 plus 0. So if you did it as 100 plus 0, what's your product going to be?
0.
So, very bad answer. Would you ever include 0 as one of your summons? No, why not?
Because the amount of them.
Yeah,
Because it would just be
it
0.
would make your product 0. Would you ever include any of the A's as 1?
No.
Why not?
Because then it'd just be the other numbers. It's a wasted number.
It's a wasted number. What could you do if one of the A's was 1?
Write the other number. It would just, wait.
So if one of your numbers is 1, it doesn't make the product any larger, so what should you do with that value? Add it to another number. Why do you think I'm saying that they have to be positive integers? Why can't I use negative integers?
Because you could do infinite many negative integers and then just complement them.
Yeah, imagine I did negative 100 minus 100 plus 200. Boy, that product is going to be large. And if I wanted to, I'll put in a negative 1,000, another negative 1,000, and I'll put in a plus 2,000. Oh, and I just get plus 100, so I need plus 100. Yeah. I can make my product as large as I want if I allow myself negative numbers. So for a problem like this, you want to think about, why do I have the conditions I do? Well, if I allow negative numbers, I can make the product arbitrarily large and it's boring. So we know that each of the a's has to be at least two. So my question for you is, we'll talk about this problem on Wednesday. We'll do a bunch more. It turns out that this problem reviews almost everything from calculus. It is amazing how many things come to bear in analyzing this. And it has applications. Now the next thing is, we still have a few minutes. So what is the generalization you could do for this problem? How could you generalize it a little bit? What could you change in the constraints? So what are my constraints on the a's? They have to be,
Positive.
not
And
what I wrote. They
integers.
have to be positive integers. We've already talked about removing positive is bad. What could we remove?
Integers.
Yeah. What if we just drop the word integer? What if we allow ourselves to just choose the a's continuously? If I told you what n is, would the problem be easier? Yeah, I'm not telling you what n is. You get the freedom, and n could be a function of the number. So if it's 100 or 1,000 or 2, you might have different values of n. So you want to get to the point where when you see a problem, you can not just solve it, but you can ask, what else can I now solve with these methods? Or maybe, how fundamental in the solution is the word integer? All right, so we have still 2 more minutes left. So I will then just mention one of the other things that we'll be doing. So I assume everybody has seen top 10 lists at some point in their lives. Letterman is famous for a lot of very funny ones. In math, we have top 10 inequalities. And one of the most important inequalities of all time is x is real, then x squared is greater than or equal to 0. Turns out this is a tremendously useful inequality. Here is another one. It's called the arithmetic mean, geometric mean, and we'll talk about this as well. The arithmetic mean of two numbers is their sum. The geometric mean is their product. Then we take the square root. And the question is, which is larger? Arithmetic mean or geometric mean? Any thoughts as to how you would figure out which way the inequality goes?
Well, if you're saying this is going to be,
Could you subtract them and then take the derivative of them and find if it's
Well,
a
so you
max
could do
or
that.
min?
But if I tell you that this is either always greater than or equal to or always less than or equal to, how would you find out which way the inequality goes?
Plug in some numbers.
Plug in some numbers. As x, if you want, we'll assume x and y are greater than or equal to 0. As x goes to infinity, this goes to about x halves. So if you take y equals 1 and x going to infinity, this looks like x halves. If you take y equals 1 and x goes to infinity, this looks like the square root of x. So by just looking at one number, in an extreme case, very similar to the baseball problem, I expect something like this to be true, that the arithmetic mean is greater than the geometric mean. When you look at your homework or your midterm averages in classes, which mean do you think we use to compute your averages?
Arithmetic.
Yeah, I doubt there's any class that calculates your geometric mean. Right? And so later in the semester, we'll talk a little bit about different notions of averaging and how do you come up with a good statistic to study. That's more important than which statistic is best. It's just having the discussion, what should we study?